Okay, so hello again to today's webinar about ventilation strategies in seconds using AI. Welcome everyone. Today with me I have Darren Lynch. He's our senior application engineer at SimScale. He will present with me and take the second half of today's webinar. And I'm Richard. I'm the product manager on SimScale on AI and our AEC offering. So without further ado, let's get started. Today we're talking about not only our fully cloud-native simulation, but also the new AI capabilities that we have developed together with our partner NAVASTO and have been releasing within the SimScale platform. With this new AI technology, people can run CFD evaluations or predictions within seconds rather than hours. And we will be showing this to you today on an example of ventilation strategy on a building. So traditionally with AI, you have the benefit of running many variations, design options pretty quickly and efficiently, which would take you days with traditional solution methods, right? So we can quickly check building layouts, the geometry orientation, how this affects the ventilation conditions, room dimensions, openings, and so on, building ceiling heights, or the different opening options like dimensions, opening and closing of certain windows. All this we will see today, and we could implement in the different AI models and evaluate actually within seconds. So quickly to the agenda. For the ones in the audience who haven't really heard yet about SimScale and what we're doing, we do a quick introduction, then what we do in the AEC, so architecture, engineering, construction area, and how SimScale is used by our customers in this industry. And then we'll see how the new AI features work, and Darren will present a case study. And then we'll leave some time, 5 minutes, for the Q&A. Okay, so quickly on SimScale as the company. SimScale, meanwhile, has about 500,000 users today. We have customers in about 50 countries. We add more than 10,000 new users per month. So it's really a large community of users, customers, and organizations. And meanwhile, we're more than 130 employees across 8 different time zones. We're trusted by our customers of being a true solution to their problems, which shows in our high ratings on G2 and Capterra, which you can review also online. What is SimScale? SimScale is a cloud-native simulation platform for the entire engineering organization, right? So what does it do? SimScale, first of all, is a platform that has broad physics. We have flow solutions, heat transfer, structural. You can model effects of radiation, humidity. So really a broad spectrum of physics. At the same time, being cloud native means there's no installation needed, right? We have instant access to the software, to the solution, also to the projects that you might develop together with your peers, with your colleagues. With that comes real-time collaboration and support. As I said, you can have a shared project with your colleagues, but also with our support staff. So you can share whenever you have a problem, shared with our support. Within minutes, they have access to the whole data set. But there's no gigabytes of data to be sent around. Instant access and instant resolution to your issues. You can run obviously simulations at any scale. Due to the power of the cloud, the computation is done on the cloud servers and not on your local hardware. So you can run hundreds of simulations in parallel. You can run small and very large simulations up to hundreds of millions of cells. And still, SimScale remains cost effective. So you can start small, ramp up to larger teams, and use SimScale economically for small but also large teams. Now, quickly an introduction to SimScale being used in the AEC sector. and how our customers use SimScale. We can see here an example of a few projects, how our customers have been using SimScale. On the top left, we see Zaha Hadid architects using SimScale for pedestrian wind comfort evaluation of a large new building in China. So the Oppo headquarters was built with SimScale as the tool to ensure that pedestrians around that area feel comfortable, but are also safe from extreme wind conditions that might be caused by such tall buildings. How we also are used by our customers is top in the middle, an example by Greenlight Building Physics. They use SimScale to get an accurate evaluation on the facade pressure coefficients. And with this accurate evaluation of the facade pressure with SimScale, they could inform the ventilation studies, the natural ventilation potential or mixed ventilation potential within that building much more accurately than with simply analytical estimations, and could provide now more value and more certainty on the actual effectiveness of the ventilation strategy of their end customer. Or for example, on the bottom in the middle, we see Adrian Smith, Jordan Gill architects, which have been using SimScale in very early stage design studies of an extremely large tower. They optimized the overall shape of the tower for reduced wind load by testing many different tower shapes, and in the end finding the optimal one. So that's more on the outside of the buildings, but SimScale can also be used for internal studies inside the building. Several examples that we see here. On the top left, our customer Curler Ronan has been using SimScale to design the ventilation strategy for a large theater hall in New York, but also for individual HVAC components like monodraught on the top middle, has been using SimScale to optimize the actual design of the HVAC equipment. Right, and in the lower right, we see a data center, a simple data center design, where SimScale also is used to optimize data center efficiency so that the least amount of cooling energy is needed to operate small up to very large size data centers. So this gives us a quick overview on SimScale and how SimScale is being used in AEC. Besides SimScale being used directly through the cloud front end in the browser, you can also use SimScale indirectly with the SimScale API. So there have been several services connected to SimScale that use SimScale in the background. So on the left side, we see Nuada CFD, which is a microclimate assessment tool integrated into Rhino directly. So you can, within Rhino, run a wind comfort study, get the results also within Rhino without ever leaving your design suite. And that's the benefit of having such an API connection. Or in the middle, we see NVIDIA Omniverse. So we have a connector where you can run CFD studies from Omniverse and also get directly the results back into Omniverse, combining it with other result assets as well. Or traditionally more in the GIS environmental studies on the larger scale. Also there, we have a prototype how you can integrate into ArcGIS your SimScale results. So what's new now with AI, right? What I've shown so far have been around since quite some time now, integrations with standard traditional CFD methods, finite volume or lattice-Boltzmann. Now we have a new option on SimScale where you take the cloud-native CFD results that you have been computing in the past, and you train with the data that you generated an AI model. With this AI model, you can predict the same solution fields, the same results as you had done with the CFD solution, but instead of taking hours, it just takes seconds. It's fully integrated into SimScale, So you can train AI models within SimScale, but you can also evaluate it next to the CFD solution. Let's talk a bit about that and what's the difference to the traditional approach. So typically how you run a study on SimScale or alternative tools, you come up with a new design and you want to test it, right? So you upload the data, you upload the CAD model, and you set up your simulation, right? Wind conditions, temperature conditions, boundary conditions on the opening of a window or closing, and so forth. Then the next step would be to potentially clean up the CAD model to make it fit for the next step, which is meshing. There's typically some headache around how to create a good mesh. And then finally, you run the simulation. And after a couple hours, you have the full results and you can review them in the post-processor, right? The 3D results, but also some key performance metrics, right? Such as air exchange rates, flow rates, temperatures, and so forth. With the new approach that we're enabling now, with AI, you have basically a two-step approach. And the step one is you take the data that you have generated, either in the past by simply using SimScale or specifically for a project. So you take that data set, which consists of variations of your design with different options, maybe different wind conditions that you did before, and you take that data and you put that through a component that we developed together with our partner NAVASTO into a graph neural network. And with that network, you train the AI model, which will then predict on a new given input, a new CAD model, for example, or a new input condition, new velocity, a new result. This graph neural network is trained on differences in the geometry, so it understands difference in geometry, but also difference in the setup, right? Materials, input conditions, and so forth. And it can also produce the same results that the traditional CFD solution could produce. For example, the velocity contours on a cut plane, the pressures on the facade, but also these performance metrics such as the flow rates or air exchange rates. And once you have basically trained this model, which in itself takes also a couple hours, then you're in the phase where you can evaluate very, very quickly a lot of different design options, right? Hundreds, thousands of designs are now actually feasible to be evaluated in minutes and seconds, right? So each new design that you then upload, you can evaluate it with the AI model. It takes just seconds, and it gives you the actual results that you need, like pressures, temperatures, and so forth. And as we have integrated the new AI model solution right next to the traditional CFD, at any point you can choose whether for a new design you would evaluate it quickly with the AI model, where you might have the drawback of getting not the highest possible accuracy, or then alternatively use still the traditional method with finite volume or lattice Boltzmann or so to get the same results, a bit more accurate, and in return it takes a couple hours instead of a couple seconds. So this gives you the flexibility in any given situation to choose the best model to evaluate your new design, either AI or traditional CAE. I hope this clears so far the general idea behind it, behind the new development. And now I'm handing over to Darren, who will then introduce us to the actual project at hand.
Excellent. Thank you very much, Richard. So yes, it's my pleasure to actually give a demonstration or walk you through an actual case study using these AI predictions. Good. So just to give you a brief introduction to the actual case study that we're going to be walking through, and I'm going to be walking you through, as the name of the webinar actually suggests, a natural ventilation study. So we're going to actually look at an indoor space, but also interestingly how its contextual buildings influence the wind flow through that indoor space. So we've got some kind of building, which is this one here, the building of interest. We've got some room with lots of openings around it, and we've got an office space where people are going to be occupying that space, generating heat, etc. And we want to understand, based upon some inputs, what is going to be the impact on that space, and how can we use AI to actually enhance our design processes. So that's essentially what we're going to be going through. And during this particular use case, what we're actually going to be looking at, varying our speeds of the wind from the ambient wind speeds, also direction, but we can also vary things like geometry aspects. So interior layouts, we can also look at which openings are actually open, which are closed, which are more closed than others, etc. And also the impact of occupancy, that is the people within the space. And we actually ran this case study a couple of months ago when we first introduced AI, but what I'm going to be doing is talking you through the story, and at the end I'll show you some enhancements and some newly enabled use cases that I think are going to be very, very exciting for the AEC industry. Good. So when we compare CFD and AI, what do we actually get? So on the left-hand side, this would have been our raw output. So this is CFD. We would have generated this using CFD, using traditional methods, and then using many, many, many result sets like that, we would have used to create our model and then predict a result that is appearing on the right. Now, in our case, we actually trained this model on 50, 60 or so inputs. We could have done much more, and we would have wanted to do much more if we had many, many different variables that were going to vary as our inputs, as we'll discuss as we get further through. But as we can see, a very good cooperation between the two, generally speaking, a little bit more smooth, but I actually prefer that in a way for my design processes. Now, let's talk about what this is actually useful for. So understandably, we've got to go through a training process. So there's got to be an advantage to training a model and using AI predictions. And that advantage really does tend to come with scale and speed. So what we might want to do is, firstly, we have an automated batch flow. We set our simulation across many different conditions. And at the end, what I want to do as a designer is understand how my ventilation strategy is going to be impacted by various temperatures, various wind angles, various wind speeds, and quickly feed back to me what these results are doing so I can make a more interactive decision. I can then go back to my design, I can vary it a little bit, upload that to SimScale, and then do the same thing in rapid succession. So it's really the speed that you're getting out of these AI models. I am actually able to turn around my design processes in a much faster way, probably 5, 6, 7, maybe more iterations in a day. In comparison to when we were doing this in traditional CFD, probably at most we were going to get maybe 2, 3 by the time we've gone through the CAD preparation process, etc., that you might be familiar with doing the traditional CFD tools. Another use case I can see this being used for, as I mentioned, would be design scenarios. So there's many different things that we can do to actually improve the comfort within our space, make it perceived to be cooler, perceived to be hotter, depending on what we're actually trying to do in what climate. And this could be things like opening or closing some windows, changing the building dimensions, the interior dimensions, or including some kind of internal obstacles, in this case partitions, or it could be internal layout of your offices. All of these can be actually changed, modified to actually improve that comfort. And it's this that we would also be able to do in rapid succession. Make a change, maybe in Rhino, our favorite CAD tool, upload it to SimScale, get a quick prediction, what's going to happen, is it better or is it worse? I go back, modify, upload. So the process continues until very, very quickly we can actually iterate these designs to improve our end goal. Because in the end, we've only got so much time that we can allocate to these projects, and the more that we can do in that time, obviously the better the end result is going to be. And the final workflow that I actually imagined those months ago was to do this at such a scale that we would then be able to generate an average yearly prediction of what is going to happen inside of the building. So we're going to be talking in a minute about things that have been recently enabled and things that are coming to the SimScale platform to do with AI. And one of those things is going to be API. So once we can programmatically interact with AI models, we will be able to create 8,760 hours, or as many as your period actually needs to be, of data. We can merge it, we can average it, and we would then get a average output for that period. And this is a great advantage because typically in CFD, what we're actually going to be doing is we're going to be taking single design hours and maybe doing 2 or 3 of those, and that's going to give us the outputs that we're going to use for design. But if we could actually get a much larger data set using AI, because we haven't got to solve each one of these simulations for a couple of hours at a time, then this would actually give us a lot more data and a lot more insight as to how we're going to be dynamically performing. So that is just talking about wind speed, wind direction, and the airflows within the space. But typically, we're interested in more. We're typically interested in perceived comfort. We're typically interested in things like temperature, mean radiant temperature, and the other parameters that are going to be feeding into our indoors comfort criteria. So I'm ahead of myself. I apologize. So I've got a quick demo here just on how you actually do this in the SimScale platform. I'll get to the exciting temperature parts in a second, bear with me. So what I'm going to do is quickly press play on this video. And we're going to walk you through what this actually looks like. So we're in a cloud native platform from the web browser. We've just created a new project. We give it some name. I'm a really slow typer, so I apologize in advance. We give it some name, we create a new project, and then we're presented with this empty dashboard where we're asked to actually upload a geometry. Now, you can upload any geometry from any CAD software. In this case, we've imported it from Onshape. We can visualize it in the viewer, and once we're happy, we can actually start setting up one of these simulations. And this is going to be very familiar to you if you've already done some simulations in SimScale before. Typical process, boundary conditions, materials, nothing's changed here. But when it gets a bit more interesting is actually when we start solving. So we're not going to solve on a computer, on a PC. What we're actually going to do is we're going to model it. We're going to use all the data that came before it. We're going to choose a model, and it's going to use the model that's already been trained to give us an estimation. Now, I've not cut this video about at all. So when it's estimating and when it's getting the data from the model, this is real time. So you can see that blue bar in the top, it's thinking, it's retrieving the information from the model. And once it's finished, it's actually going to populate in a little disk in the middle there for me. So this usually doesn't take much more than a couple of minutes. So as you can imagine, if you had a few of these geometries set up, and actually this entire video is about 2 minutes long, if you had a new geometry set up, you could very quickly upload it to the SimScale platform, set a simulation up, get an estimation back, and make a design decision based upon the results that we're actually seeing at the moment, and very, very quickly. So this is velocity magnitude that we were actually assessing there at the end. Now, that was very quick. Obviously, you've got to train the model up front, and that can be automated using the user interface or also the API if you wish to do so. But you can imagine if you have a company where someone sets these models up for you, and you as a designer consume those models to help you quickly iterate your design processes, this is going to be very, very powerful. Good. And I give you the prelude to the heat transfer solver before I actually got to the slide. So I apologize. I was talking about temperatures and how those impact the comfort. And that leads us on to a very interesting enablement for the AEC industry, and that is our AI model is actually able to support the CHT version 2 solver. What that actually means is not only can we solve all of these fields, so we've actually enabled mean radiant temperature and humidity recently into our conjugate transfer solver. So spatially, we can assess using computational fluid dynamics, speed, temperature, mean radiant temperature, and humidity, all coupled in a single simulation, which is really advanced. I really love this new capabilities. And then on top of that, we can calculate fields such as operative temperature, predicted percentage person dissatisfied, and also predicted mean vote to understand what the perceived comfort of a person actually is within those indoor spaces. And our AI model has been recently enabled onto the CHT solver, so now we can actually predict these results using our AI models. So that's where I kind of see this going. And as you can imagine, this then opens up the fields not only to just natural ventilation, but also many other use cases as well. And I know that we said we would leave 5 minutes at the end, so let me buzz through to the next slide, and we'll talk about question and answers. Also, we will be following up with recordings and material, so all of these further readings will be sent out to you as well. So we've got further reading here, many different customer cases that you can read and understand how SimScale has been used in the AEC industry. You can also check out some of our validation studies for many different use cases in the AEC space. And we're finally on to the Q&A section. So if you haven't already, and I'm sure you've got loads of questions, if you haven't already been typing your questions into the chat box, then please start doing so. We're going to dedicate the next 5 minutes or so to answering those, and I think Nagman is going to join us to moderate that part of the webinar. So welcome, Nagman.
Hi,
Darren.
Thank you, Darren.
Can you hear me?
Yes, I can, Nagman.
Yeah, brilliant. Thanks so much for a fantastic presentation, and to Rickard. I mean, this has opened up so many possibilities in the AEC sector, and really, there's a lot of questions around AI in AEC. You see it everywhere, right? LinkedIn's full of comments around AEC, AI, lots of new startup tools. I think what we brought here, there's so much interest in people on how to get started with it. So I have a few questions from the audience. I'll skip through those and I'll hand back to Rickard for some closing remarks. Yeah. Okay, brilliant. Let's take some technical questions first, and then we'll move on to the industry level ones. Darren, you showed a slide just at the end there about CHT where it had PPM, PPD, operative, various other bits that were involved. Would solar be included in that? Calculating solar gains, would that be connected to the AI side eventually or now?
Yes. Yeah, it's, correct me if I'm wrong, Richard, but it's currently enabled, so it's included in our radiation modeling, and that means the MRT field as well.
Okay,
Yep.
fantastic. And are the features that you've shown, they're available now to use, or how would you suggest someone get started with what we've shown them?
I think everything that we've shown in this session is already released. So we recently released in the last couple of weeks the enablement of the CHT model for our AI workflow, I suppose we call it. The best way to get started, I would say, if you're already a SimScale user, a SimScale customer, then reach out to your customer success manager. They can point you in the right direction, make sure you're rolling. If you're not a customer currently, then please do reach out to us, sales@simscale.com. We would be more than happy to discuss your needs and see if we can help you out.
Fantastic. We have a bunch of questions coming in from the attendees. So we have a attendee asking, are the MRT calculations fully AI enabled with the model's input?
Richard?
Yes. So in a sense, maybe to clarify, the current generation of AI models we're using are graph neural networks. They're fully data driven. So in that sense, the AI model doesn't understand the actual physics and if it's MRT or if it's velocity or it's a different field. Basically learns from the past data, from the inputs, the results, and the geometry, and it correlates that to make the prediction for a new result. So in that sense, it doesn't really matter which field we're predicting. If it's in the training data, the model will be able to also predict it in the results. That's not telling that for all the different fields, the quality of prediction is the same, right? So different fields have different sensitivities with respect to the input. So some might be easier to predict and others might require more data to get to the same level of accuracy.
Ricard, related to that, we have another attendee asking how many simulation models and how much data is needed to train the AI model? And is that something the user does, or will you do that on behalf of the customer?
Yeah. So it's hard to quantify, to give it an exact number. Typically, we start around 50, all right, around 40 to 50 simulations to see how the model is performing, and then we might add more data if the desired result quality is not yet achieved. The data can come either from past simulation data on SimScale you just generated with the normal work you did, or we might run a project together, right, to support you in generating new data, to have a better data set for AI training. The good thing about the models we use is they're parameter free. So it means you don't need to, in a specific way, design your simulation setup so it can be used for training. Right, you can just run normal simulations as you always do. You don't need to add a parameter or run it with a specific API configuration. Yeah. So if you're interested, you have a use case, let us know. We're happy to explore and maybe get a first prototype running together.
Brilliant. And the demo Darren showed, that looked like quite a simplified geometry. So another question is around the complexity of the model and its, I guess, how useful AI is there. So how complex can the CAD model be for this to be, to actually use and get value out of this AI approach?
Yeah, so I think it's good to remember that what we're showing here isn't the lattice-Boltzmann method, the one that we traditionally show that is robust to geometry. So there will need to be some level of cleanliness to the geometry, but the level of complexity can still be handled quite well. In that sense, buildings, if they're built correctly, then we could have lots of them with details, etc. And it's also good to know that we have got an immersed boundary method that we're working on that's almost at feature parity with conjugate heat transfer version 2. So for more dirty geometries, we are looking to move those towards the other conjugate heat transfer solver. So that's going to be a very good one for the HC industry.
Yeah. And just going back to training data, does SimScale provide pre-trained models for customers to use for different use cases, e.g. external flow, internal flow, etc.?
Maybe Richard, do you want to answer this one?
Yeah, currently not. The models that we're currently doing are very targeted for specific applications. So it doesn't make sense at this point to share them more broadly. We plan actually to release a pre-trained model which is for a use case that is more comparable across different geometries, which is the pedestrian wind comfort module, right? Where you always will have some kind of building, some kind of city with a very consistent simulation setup. For that, we also have enough data. For other more generic use cases, like, I don't know, stress analysis or indoor ventilation, we currently don't offer a baseline model. But yeah, we're working on it. It might take a bit more time to have a useful model, right? That's the main thing.
Fantastic. Let's take. I'll take two more questions. One for Darren, one for Ricard, and then I'll hand back to Ricard. So, Darren, can this be used now or in the near future for sizing purposes? So if there's an opening, a ventilation, because the demo case you showed was about ventilation. So sizing of openings is still an important thing when it comes to design, right? Like the free area of a ventilation grill or a window to get a required ventilation rate for a particular, use case, like, a classroom, for example. So could this
Yeah.
be used and applied for that? And I'll ask the next question quickly to Ricard as well. Ricard, if you're looking at someone like a computation designer at a large AEC firm, who's used to, visual scripting, and they use tools like Ladybug, Grasshopper, Rhino, a bunch of other tools, where would this fit in with their workflow? So I'll leave you guys with those last two questions, and then I'll hand back to Darren and Ricard.
Thank you, Nagman. Maybe I answer mine first because it came first. Yeah, I think that's in our current capability set. So we would consider the sizing of the windows to be a geometry change. We can already predict what would happen if the geometry changed its dimensions or its shape or its size or its positioning. So yes, that's within our current capability set.
Yeah, and regarding the second question, so I'm thinking that such a methodology, such a tool would be most useful when you have a large development where you have so many options to test that are potentially improving certain aspects of the design, but might also at the same time counteract each other, right? So you increase the window area to get more light, but then you have issues with thermal comfort in the winter, with heating requirements and so forth. So in such complex scenarios where you have still a lot of freedom and where the project is big enough to justify and actually require such an optimization process, there such a technology is the most useful, because there it's very efficient to run thousands of different design options, right? And you can spend basically the effort to prepare the initial data set that you still need to run on traditional CFD to train the initial model. But from then on, you can quickly iterate with the actual end customer, right? With the architect in the room or whoever is actually using your simulation results to live basically try out different options and see the impact on many different KPIs.
Yeah, Ricard, just on that point quickly, a lot of people who would be using CFD will also be using thermal modeling tools, right? Like IES, Design Builder, NG Plus, for things like, sizing, ventilation, overheating calculations, compliance as well. And previously it's been, as you know, right, you and Darren both know this, you've worked on these problems a lot. It's always been quite hard to combine the two, right? We've had many cases where you're trying to input CFD results into dynamic thermal modeling tools. Where do you see this fitting in now with that whole ecosystem of tools, basically?
Yeah, I mean, the underlying functionality, right, and how to integrate tools hasn't changed. But what changes with the introduction of AI is the actual responsiveness of a solution, like SimScale or CFD in the background, in combination with an energy modeling tool, right? For energy modeling, you're used to evaluation times of seconds, right? If you change the design, you would actually get different pressure coefficients on the facade. But if you wouldn't then need to run a full-blown CFD study, you might wait a couple hours, right? And by the time it's not sure, right? If you have the time to iterate over these many design options, right? So in that sense, it changes a bit the usability of SimScale or CFD solutions with AI in combination with energy modeling tool, because the response times are then the same scale, right? Which before they weren't.
Yeah, absolutely. Okay, amazing presentation. I think there's a lot of interest here, Ricard. Darren, thanks so much. I'll hand back to you, Ricard, for some closing remarks.
Yeah, thank you. Thanks, Dagman, for the great Q&A. moderation. Yeah, what are the next steps? If the presentation sparked interest and you see there might be use cases for your organization to try out SimScale or the new AI solutions, yeah, feel free to book a demo, go to simscale.com, contact us, or directly write to me or Darren, dlynch@simscale.com, or to sales@simscale.com. Reach out. We're really happy to do a one-on-one demo, show you on your use case how this would work, evaluate if that is feasible for the project in mind, and yeah, start from there. That's always the first step, right? To actually evaluate if it's the right solution for the problem at hand. Otherwise, the traditional CFD solution won't go away. That's still the baseline also for any AI model. So if it's not AI, then it's still very likely we can solve with the traditional CFD methods we have that are very powerful and come with all the benefits from being cloud native. And with that, yeah, thank you to everyone that's still watching. You will get the recording via email in the coming days, and see you hopefully next time for the next webinar. Also, thank you, Darren, for the great presentation today. Thank you.
Pleasure. Thanks very much.